Yeah, welcome to this workshop. So, done with the help of the Mark Stevens, cryptographer, who's the author of all these attacks, regarding whether it's MD5 or SHA-1. And in case you have downloaded the slides some time ago, make sure you have the latest slides, but most likely it's not a problem. And if these slides are, I improved significantly the slides over time. It's the 5th time I'm giving this workshop. Don't hesitate if you have questions, and I will also update the slides if there are unanswered questions. And the slides, as mentioned, is available on Speaker Deck at this address, so you can have a local version that you browse yourself. And let's make sure that everyone has different knowledge, right? And so if someone next to you will do a check just after that, but if someone next to you has less knowledge on something, feel free to help them. It's better for everyone. So who knows or who doesn't know what is hexadecimal, hex viewing, NDNS, and this concept? Who doesn't know? Everyone's more or less familiar with this concept? Who has already computed hash collision attacks? Okay, 2 hands. 3. And then you're familiar with basic concept of file format, like they have a magic, some header, footer, this kind of thing? Okay. And hash functions, MD5, SHA-1, the way they work by blocks and so on. Okay. And anyone has done some file format abuse besides Floyd? File format abuse already? Not so many. So really, again, we're more in this. Some exceptions, but really this is already covered. So I don't need to explain in detail what is everything about hash. And just one thing, hash clash is actually the name of the whole project, but the chosen prefix collision about hash clash should be called hash clash CPC, but I just shorten it to hash clash, just fixing stuff. Anyway, it's me. I love file formats. My license plate is a CPU, my phone case is a PDF, and my resume is a Nintendo Mega Drive polyglot. And I'm working at Google, and I love file format anyway. I'm interested in all aspects of file formats. And as we saw, we all know hash collisions, hash import. So I will not have to cover that, I think. There's just a big difference between hash collision and password cracking. You have a hash, you want to find the exact string that creates this, it's password cracking, but there is a lot of constraint regarding the original length and content of the password. And hash collision is about creating 2 contents that have the same hash. And very, very important, these hashes are not known in advance. You don't aim for a given hash, you just make 2 contents have the same hash, and you don't know what the final hash will be. This is like very important, it's something people don't get. So we will not know, we will not say, hey, we have the hash of Notepad, we want to have a file with this. This is not hash collision. This doesn't exist in practice. I'll insist because people really have a problem. So again, getting a specific hash, it's called a pre-image attack, and it doesn't exist for MD5 SHA-1. It doesn't even exist for MD2, which is very old. It only existed for a few cases where it was demonstrated, but that's very rare. So it's not what it's about here. The thing is, with some file tricks, we can instantly generate files with the same hash. So we will combine the known hash collision attacks with some file tricks to speed things up. So even on the web page, there are already examples. So already created stuff for instant PDF collision, video, images of different formats. There are some limitations sometimes, but it's really, you just download these videos, you run a script, and it's really instant. Also work with GIF, and quite funnily, it also works with Windows executable. So you can instantly get Mimikatz and Cuphead.exe colliding the same hash, or you can even do that, we'll show that with different file types. So JPEG and PE. So I send you want pictures from a holiday, I send you the file, and you download it because you wanted to see the pictures of my holidays. And then there's a Mimikatz executable, and now you whitelisted it. Because if you're whitelisting by MD5, that is. So just new collision, I'm not sure you can see, but colliding 2 PNGs really takes like less than a second, because I already did a collision computation, and now it's just moving buffers and just putting things together. So it's combining tricks. And in some cases, like the PDF, the colliding files are 100% standard from a parser perspective. So it's just the file have a very weird structure, but the files in their parsing, they will produce no warning. They are just valid. Another myth that is usually when people compute collisions, they compute two files of the same file type, and the files are very different, because that's usually people demonstrate yes and no, or one of the first examples when we released the SHA-1 colliding proof of concept, someone collided Donald Trump and corn with the hair of corn like this. So, you know, it's really very different, but it's wrong. And you can actually collide more than two files or files of different file types. So if you know POC or GTFO, the issue 19 is 4 file types of having the same hash. It's a file that has 4 types. And it's an executable, an image, a video, and document. So it's 4, and really it's very different things. So these 4 things, the magazine and the PDF viewer to view the file, and a video, and this image, all have the same hash. And we didn't need recomputation every time. So computation took some time, but after that, whenever we modified the LaTeX, it was just regenerating again its instance. I mentioned earlier that usually the colliding files are very different. Here, this is the opposite. On the previous issue of POC or GTFO, issue 14, we just added 609 collisions so that you can change the number that is displayed on the front page, and then you can just adjust this number to display the actual MD5 of the file. So it feels like a magic trick, but it's just you can flip these numbers and the MD5, the overall MD5 will not work. And this file is a PDF, but it's also a Nintendo ROM, and the Nintendo ROM also shows its MD5. That's why there are 600 collision, which is a bit too much. On the other hand, it means that with this file, you can easily, by flipping bits, you can really easily generate 2 to the power of 600, which is like 400 digits or something, having the same MD5, which coincidentally start with seafood. So really, this is a demonstration that it's a standard 60-page document, and only a tiny part is actually using hash collisions. It doesn't have to be the whole file. And also it works with SHA-1, but as far as I know, there's only a single computation of SHA-1. And there is no other, even the tools are not available, sadly. And I just reused the prefix we computed for the public collision at Google. And you can reintegrate it into any document, such as here, the issue 18 of POC or GTFO, which has the same SHA-1 and different images on the front page. And again, the rest of the document is identical. It's just colliding an image inside a whole document. It's just an image that can change without modifying the SHA-1. So it's not new attacks. There are shortcuts, file format shortcuts that are needed to have this instant aspect. There is one attack that is super fast, and we'll see that it's very hard to exploit. So we'll see why. But all these other computation, like this attack took 6,000 core years. So that's a lot of time. And this is combined with file tricks to make it instant again with new files. Any questions so far? All good? And the good thing is that whenever you find a new trick, it will be reusable, likely for SHA-2. So if someone then starts saying, oh, we'll compute SHA-2 collision, maybe one day, then you can reuse some tricks, because file formats don't care about which hash you broke. And the same, the hash doesn't care about the structure of the file. So it's very orthogonal, so it's quite fun. And some tricks, some file formats don't have suitable tricks, no shortcut for ELF. So you can do like any pair of Windows executable in the collision, but there's no such shortcut for ELF because of its structure. Because very early in the file, the architecture is there. So you cannot put collision blocks before. I'll explain what it means later, but just if you have an idea of ELF files. So the goals of this workshop is having some idea of file format structures and the manipulation, and understand not hash collisions, but their attacks and how you can exploit them. And then create your own exploit. So basically, you're doing a pen test, and you see a system that is indexing file with MD5. What can you do? I already put some scripts available, but they are indexing another file type. Can you go from a few hours for a pair of files to instant collision, in case you demonstrated some knowledge? It's quite good, because when you say, hey, I created instant collision for this file format, people are usually convinced. It's good because it's not a bug, it's not a bug that can be patched. It's like, if they're indexing some files and then you produce instant collision, then they are convinced that it's not reliable anymore. And yeah, people say, but no one uses MD5 anymore. And just in July, WeChat was actually filtering files censorship via MD5 of the images. July this year, so a couple of months ago. And yes, maybe you heard of this, the shattered attack, so the SHA-1 collision. And I took part in it at the file format, and here are all the documents on the related to this attack. So Mark is the author of the crypto attack. It's so complex, it's not funny. It's like, if you don't know what boomerang bits or neutral bits is, yeah. Pierre is focusing on computation, which is interesting. He's comparing the amount of energy spent with the amount of water it would boil. And I think for SHA-1, it's like, the units of water is Olympic pools. So he starts with teacups and whatever, teaspoons of water for this attack and whatever. And then this attack, 3 Olympic pools. So it's actually interesting. And I have a talk on file formats. Actually, I gave it 2 years ago here at Black Alps. So using hashes for using MD5 is not necessarily bad. It depends what you're doing with it. But more importantly, if people control always the input, then you don't know if a file that is whitelisted and is considered clean now couldn't be another malicious file later. I mean, unless you actually have some analysis of the file itself. So basically, blind indexing of files that are user controlled, nope. But on the other hand, there are some use that is just okay for MD5. And again, yes, you encounter a system that uses MD5, you collide the normal file, and the good thing is that a few hours of research, you analyze the system, you analyze the file format, a few hours of computation, within a day, you can demonstrate that maybe the system is not reliable at all, which is good. And again, I prefer to do the talking. You can convince people all you want. When you give them, here is a script for instant collision, it's funny, you have nothing to say. So, and I also liked that hacking a file format, MD5 collision is just getting to know a file format, but just the surface. But it's the usual tricks for file format manipulation. So if you're not familiar with file format manipulation, it's very good because we won't understand in depth how the file format are, because that's not required. And that's typically a mistake that people do. They start to dig and in the whole file format, and they open 101 editor, and they have suddenly the whole header structure. And it's like you're flooded with information, but it's totally not required. So don't be scared. It's not a crypto talk. I don't know anything about crypto. So I probably say wrong things about crypto. Definitely, Mark, the link to Mark thesis is there. I will make some reference there, but yeah. For questions about crypto, ask Mark, please, or not me at least. And yeah, again, I really don't understand. And we just reuse existing attacks, and there are only 4 of them. So it's easy, like I think we can all count to 4 and we'll cover all of them. And you don't have to be an expert in file formats. Really, you don't have to know how all these things work. You just need to have a very, very basic understanding of a structure. So it's less complex than some Lego models. And even if you're familiar with my posters, this is too much because this is already detailing too much information about this tiny file. We only need to understand really the overall structure. We don't care about the things. Which is like, if you review it in the hex editor, it really feels like block, which is why I call it call trace, because it feels like a puzzle game. This is how I see my file manipulation. It's just, you index stuff and you move the block, and then at the end you have the same hash. Thanks, Mark. He's doing the hard part. I have a topic on a high-level introduction on the topic, which is called Kill MD5, which is already available. But this one is no hands-on, no hex. If you want to explain someone the problem, but we will do the hands-on part. Any questions? It's on YouTube, and it's the links are there. So the slides are on speaker deck, and the video was recorded by Cooper, of course. Released 20 minutes. A round of applause for the almost on. Come on, come on. So yeah, you said you already know the basics of hexadecimal. I don't need to cover this. ASCII encoding, NDNS. It's important. We'll see why later. I mean, it's important. Yes. Just a small. You're familiar with hex viewing this way. Very important thing. We will need to have exactly the right adjustment because of the size of the block. And some hex viewer, when you resize the window, they will not wrap at 16. And then you will be confused because you will need some stuff exactly at the 10th byte and not at another offset. So make sure you always wrap at 10. Okay? In hex. Okay? Because otherwise, you will do your computation and it will not collide, and crypto doesn't care about these details. Because yes, some people ask me, oh, it's you have to put at the 10th byte. Can I put at the 9th? No. Crypto. So I mentioned the final, I insist, the final hash is not known in advance. We just have two contents and magically get the same hash, but we don't know which one. So has anyone done the prerequisites or need help or something? So you don't need to, again, you don't need to have the tools ready to compute the collisions if you want. You can directly, I will see that later, you can directly get the prefix that I computed. It's up to you. But it really feels magic when it actually works. So again, if it doesn't work, compilation or too slow, all the prefixes are again on the same repository. But on the other hand, if you download just fast call, but even the Windows binary, and it works with Wine, and it doesn't fail, and it works, it feels like magic. Oh, not magic, just tricks. But yes, it's pretty funny. You download the binaries, you just run them with Wine, and it works. It should be like, it should take only a few seconds. And of course, it's better if you have a file format manipulation environment. I will introduce one use and to you now. A copy of the workshop materials and a copy of the slides. You have the URLs here. I mean, not the full URLs, but how you can search them on DuckDuckGo. So GitHub, Speaker Deck, GitHub Core collisions. If you want, GitHub CR Mark Stevens hash clash. Can I go on and you do that in the meantime? Or someone needs help? Okay, move on. So if you're not familiar with hex viewing, I'm just going to suggest one now. I don't know if you're familiar with Kaitai, but it has online viewer, which is very nice. So it's used YAML-based parsers, grammars, and many formats are already supported. You can drop. So I will show screenshots. So it looks like this: ide.kaitai.io. So it's like this, and you have some grammars already available. You can edit them live. And when you edit them, they will save as a modified copy on your local storage. And you can drop the files and they will directly be there. Now, another thing I mentioned earlier is that these grammars are complete, which means they give you a lot of details that you probably don't want. On the other hand, removing a lot of information from this grammar just to display the basic information you need is certainly a time saver, which is exactly what I did. I provide also in the workshop materials simplified grammar just to cover what you need to understand for collisions. You don't need to go into the whole detail of this thing. But it's really good, and it's available online. And there are also command line tools if you want to apply these YAML grammars to any files. So if you didn't know Kaitai, definitely check it. And now Trail of Bits released this week a tool called Polyfile, which is also compatible with reusing Kaitai grammar to parse files. So it's like really useful. And to be honest, when I study a file format, I open the specs, but I often look if there is a Kaitai grammar, because at least very quickly you see what the files should start with without having to browse through thousands of pages of PDF. So definitely, if you didn't know Kaitai, that's a great repository of knowledge. Also, this very nice interface. And really, I study the grammars for details, especially because, I don't know if you see here, but they also reference the exact URL regarding this element of the file that they dissect. So it's really well done, really useful as a knowledge base and as a viewing tool. It's not an editor. You cannot edit the files inside, but it's still very good. So if you're not familiar with file format manipulation, skim through the specs, just have an idea of the high-level structure, then look for possible forms of manipulation. If you can remove or modify in an unwanted way the structures to suit your need, so parasiting, or you can move structures around to your benefit. It could be helpful. And of course, always check open source, standard open source implementations, because you might have surprise. The files of the SHA-1 collisions are actually invalid because they break in theory invalid because they break a rule of the official specification. But in practice, libjpeg is fine with that, and libjpeg is everywhere. So if libjpeg doesn't see anything wrong, the files are valid everywhere. So don't follow the specs too much. Look at the actual implementation, and of course, at the fragmentation. For example, if you want to hack a PDF, there are like 6 families of PDF viewers. You need to adapt to all of them. But for JPEG, there is libjpeg everywhere. So if libjpeg is happy, the files are valid, even though the spec says they're not. If you want to diff the files, you can either use diff and xxd, that is fast. You can try vbin diff when it doesn't segfault, or a very good radiff from Radari, which is pretty cool, which is only showing the modified lines with some context. Pretty cool. Just so that you make it easier to visualize the differences between 2 computed prefixes. So, our first block. Identical prefix collision, which is fast call. First warning, collision computing is a very random process. People just expect that it runs and finishes. No. Sometimes, actually, one of the parameters is seeded on your time, and depending on the value, it can take 0.3 seconds or a lot more, 13 seconds on the same machine. It can really take, you can be really lucky, it can take 2 hours for big computation, or 15 hours the next time. So don't worry. First, it depends on your system. And sometimes the result is different each execution, because basically computing a collision is just trying some stuff and verifying some equations until all the equations are verified. And if it's not verified, then continue the loop. It's like a big loop, and it retries a lot. Okay, so really, people just expect it's always the same time, and the computing time from one machine to the other could be like very different. One thing is that we will not use anything that requires GPU acceleration, no CUDA. So this is not making a difference here. And actually, the SHA-1 attack was one big step with the CPU only, and one big step with the GPU. So underneath, it's complex. We'll skip that. And sometimes, with some collision, it just doesn't work, so just retry. Okay, so let's start. And so who is willing to try to compute and has a fast call ready to compute and wants to? Compute either the binaries, either the Windows binary with wine, or, okay, not so many hands, like no hands. Okay, so we'll do in total theory mode.
No, I would like to try it, but
just, I mean, this is just easy, right? This takes, it can take like a few seconds. So if you had Git hash clash already, just try to compile it or get the Windows binary, or maybe we'll do later. But in the meantime, I'll take some water.
So hash clash is sufficient?
Hash clash, yes, has all the attacks.
Okay.
This is part of hash clash. This is a hash clash has a fast call, unicall. and the CPC.
It's compiling.
Still combining.
Okay. But when you do that, just now?
Yeah, so I cloned the Git repo and compiling. I mean, you can go on.
Yeah.
Fastball minus PM.
Any questions in the meantime?
There's releases. But also
So just create an empty file and just run it as a prefix. Like there will not be any prefix before the collision blocks. We'll see what it means later. So I'll move on. You obtain something that looks very random, very high entropy, 2 blocks with only a few differences, very few differences at very specific offsets. Okay? So the content is totally cryptic. The content is different, but they have the same hash. Yeah, just I can actually show you what it would look like. It only takes a few seconds, so I mean, it'll run time. And this, tuck, 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 tuck. And then it's done. And they have the same hash. So it's really, and fast call always works. And they always collide in the end. So it's really very, very, very fast. So 2 blocks of 64 bytes, totally random, and a few tiny differences. And all the rest is identical, which is why I show it like this. Now if you run it again, it might give a totally different time, and the result will be completely different, still totally random. So the ASCII column is totally irrelevant, but the differences are exactly at the same offsets. So a hash collision is a big pile of computed randomness, which is why the final hash is not known in advance. This is full of randomness. We have no idea what at the end we can compute the final hash, but we are not trying to aim for a specific hash. This is not what it's about. Yes? Offsets? Exactly. Because it's it's because of tricks in the MD5 structure. So they will be exactly at the same offsets, which is why it's predictable, even though some part is predictable, even though there's a lot all randomness. And even the value here will be different, but you will know what the difference is. Yes?
So it's a basic question, but like, say you don't want to go for a specific hash, because it would be computationally much more difficult to do so. What's the,
Yeah, it's a totally different exercise.
Okay. And computationally would be more difficult to do.
Just much longer. Here it's instant. And it's still a big hash, and it's still a lot of data.
So we can say this is exploiting the weakness of the hashing.
Yes, actually, I think I mentioned later, but there is a story behind the first MD5 collision, which was found by a Chinese woman, a Chinese researcher, and she found these shortcuts by pen and paper by looking at the specs for an incredible amount of time. And there's a very good background story, because initially there was some misunderstanding, so it didn't collide and whatever. It's an interesting story, but pen and paper, like what? Mark Stevens think it's normal. I can't do that. I cannot. I definitely cannot. Let me know if you can. So yes, the differences will be always at the same offsets, which is why if you plan something to aim to, you rely on these bytes, exact bytes, you know the difference is there. Yes, this is the YouTube video regarding the initial finding. Yes.
It's easier to do some images because you won't be very noticeable, right?
Sorry?
It's easy to do this this on images because it won't be very noticeable. Because there will be so tiny differences in the image, right? But if you do this on like some more like text or something like that, that also would be very different.
This is totally generated by the tool. So this is like added to the file.
It's a patch.
Yeah, because the original file you supplied is empty. So this is just the result of the computation. And all the collisions attack are just computing some stuff depending on what's before, and it's full of randomness. So you cannot, I mean, we will see, but this, you cannot, you don't know what will be there, it's randomness. So now, okay, if you put a prefix, just anything, and you can supply it to the collision, to the computation, the value, the prefix, very important, the length of the prefix, whether it's null or super long, whether it's full of zeros or high entropy, doesn't change at all. The content of the prefix will just set the initial value, and it doesn't make any difference in the speed of computation. So collision speed doesn't depend on the original content of the prefix.
Is it because how MD5 works with blocks and the last block?
Yes. Spoiler. So what we get as computation is exactly what we ask as a prefix. Then there is some padding to the end of the next block. We'll see that later. And after that, added our two blocks of 2 times 64 bytes. So our prefix, whatever it was, some padding, which is here full of zeros, but it could be full of anything. And here again, collision blocks with again the same differences at the same local offsets. And if you notice that it's 2 blocks and the local differences are the same per block. Any questions? So this MD5, SHA-1, SHA-2, they work with blocks of 64 bytes from start of the file to the end. And they always how do you say? And there is a property that if at a block boundary, these two things have the same hash, whenever you add something after that, the hash will remain the same. This is very important. So you see really why we speak in blocks, because we know these blocks are 64 bytes, and if you align them, it's 4 lines, so it's really Tetris. I mean, Coltris. Yes?
Sorry, can you repeat that? Then you have these specific blocks, everything which follows doesn't matter for the hash.
When you have 2 files, and they have the same hash at the block boundary, at this point they have the same hash. Because it works from start to end with blocks, if you add the same thing, if you have the same thing on each side, it still maintains the same hash. So like, yes?
So that's why in the tool you can only provide the prefix in the structure.
Yes, exactly. And the computation depending on the exact content of what was before. If you modify a single bit, the computation has to be redone from scratch. No shortcut. Which is why once I did a computation that was took 2 hours, and I had like 1 bit wrong, and I had to retry the computation after fixing that bit, and I was a lot less lucky on the second time, and it took 15 hours. So from 2 hours, 15 hours. So plan your prefix well. And this is also why I spent a lot of time double checking, triple checking. I don't know how many times, what would be the SHA-1 computation. Because 6,000 years, I didn't want to screw that up. And I almost. So all these attacks work with those alignments, and then the padding, then adding at block boundaries an amount of block, from 1 to 9 or something. But always it works by blocks, which means via these attacks, every pair with the same hash have the same length. And the end of the file is either identical, if there is a suffix. If there is this case, then the end of the file is identical. And if you go back up to the collision blocks, then there is high entropy and differences at given offsets. So if you look at the end of the file, and they have the same length, and if you look at the end of the file, it's very suspicious. And this is the case for all these attacks, including the SHA-1 one. Shattered. So we always work with 64 block. And again, double check your hex viewer wrapping to not waste time. What's wrong with my blocks are? Because some hex viewer do that. So congrats. So when you reach that point, you completed your first hash collision. Print your own certificate. Any questions? So as a recap, we define the start of the file. The computation will depend exactly on its content, but what is inside doesn't matter at all. It's crypto. It will not do any analysis whether it's French or random data. Then there is some padding, which is just to get at a multiple of 64 bytes as a block boundary, and it could be full of zeros or it could be your favorite ASCII art, because that's what I do. It's just here to align things to block boundaries. And then this, depending on what's before, some blocks are added, depending on, and full of randomness with a few differences. And these blocks will only work for that exact prefix. And then after that, since you have the same hash at this point, you can add whatever you want. On both sides, it will keep the same hash. So an identical prefix hash collision, so an IPC, is whether it's a fast call or another IPC. It always takes a single input. And because the prefix and the suffix, if it's there, are identical, only the very few indexes, values in the collision blocks will be different. So the two files are like almost identical. Now the trick is that you still want them to look very different, even though they have only a few bits of difference. Does that make sense? And again, this is common even to shattered, or to all the IPCs that are here. So what can we do with that? We need to have the right alignments. Then we need that the randomness is not a problem for the parser. We need that this tiny difference have an impact on the parsing. And then, again, whatever we put afterward will be ignored, but that's appended data for file format. That's pretty common, but the rest is very hard. So I think it's pretty clear why it's so hard to exploit fast call. Because the start alignments, how do you say? Oh yeah, tiny difference, yeah. Yeah, I think we covered that already. So fast call, it's hard to exploit because the differences are in the middle, surrounded with random data, and that's the only difference between your two files. So there are very few file formats that actually work with that. And there is one in the slides, but we will not cover because it's a bit too hard. But if you want to spend more time on the slides, it's explained. You have a question? Okay. Just scratching your back. So why is it so difficult? Because differences are surrounded by random data, and you should declare a structure, a valid structure for the file format, and at the same time, something that is different, that makes a difference in the rendering with a single byte that you don't even know the value, that is surrounded by randomness. So one thing you can do is that, on the other hand, if you run some code, you can just check, hey, is the bit here set or not? And then have two behaviors. That's a trick, but it also works. And this is how, for the SHA-1 collision, the files also had a JavaScript payload that was checking the different, the value here without knowing them in advance, but just having two different behaviors, evil or good. And then you send the good file, you get isolated, and then you can send a malicious file. Another workaround is just do brute forcing, or if you remember, I mentioned how that collision computation is a very random process. So you see it's really a while with a lot of, if this not equal to this, then continue. And if this, it's really trying a lot of things. And you can, if you want to have smarter brute forcing, you can just add an extra condition so that your brute forcing is just not totally dumb. That's how, This was demonstrated by SPQ in one of the articles of Poker GTFO. But we don't need to actually do that, because one day I was like, there is this fast call that is super fast but hard to exploit. There is hash clash that we will see later that takes hours is super powerful, but still takes hours for a pair. And then I ask Mark Stevens, do you have something in between? Something slower, but that is more potential able. And thankfully, he created Unicode. So for fast call, important so far, instant computation doesn't give instant exploitation, right? We need, because fast call is the only instant, almost instant computation, and it's impossible to exploit or almost impossible to exploit. So we need to combine all the stuff you saw with PDFs and other formats. We need to combine that with file format tricks. Is that clear? Sorry, you had a question? Okay. So now we need to know what kind of file format tricks we need. So basics of file formats. From a high level, a general structure of a file format in general is that there is a header at the start of the file. It defines the file type, and it also gives some information about the files, like the dimensions, the color space, the video duration, this kind of thing. It's metadata. But then the important data is in the body, which comes after the header. And this body can actually, in general, it's really as a single thing, but it's actually made of several objects that can be moved around, which is very important. And another thing is at the end of the body, once all the elements of the body are present, there's a footer. And the property of the footer is to say, this file is complete. And whatever is after the footer is ignored, which is very useful so that we could put some other extra random data, and it will be ignored. The file will still be considered valid. So these formats typically accept comments. And a comment usually is just a text, a single text about the URL where you downloaded the file or anything. But in practice, comments can contain anything, like random collision blocks. You see where this is going. Or they can be any arbitrary length, which is perfect for aligning things. And the good thing is that they are not counted, like usually there's only one comment per file because it kind of makes sense. But in practice, they are just ignored. So a comment block, typically for a file format, just means ignore the next X bytes. And if I created a JPEG with 2,000 comments, if you see why, let me know. You earn a prize, my bottle. But it's possible. The parsers don't care. They don't count the comments. They don't validate any of the data that is inside. And the file is still valid. And these comments, usually, they are before the comments, this space, this ignored space, the length is defined. So if you align this length declaration with the collision difference, then you see that the length of the comment will change, which means you will jump a different distance. You see where this is going? They can provide padding, they can provide ignoring randomness, and their declaration makes them of variable length if required. And you can use them as many as you want, and here you need 3. So you see where this is going. We need to have 3 comments. A typical misunderstanding of parsers in general is that usually on your computer, on the internet, the files that you download are valid. They are perfectly ordered, like it's made by Germans or Swiss. It's like perfect, and there's not a single wasted byte. But in practice, because there are all kinds of libraries, the parsers that you typically use have to be much more resilient than that. They don't expect a perfect file and suddenly they don't work. They actually behave like a detective, as if you're in an escape room and you have to gather the hints, and when you explore everything in the room, you have the solution because you gather all the hints. And in which order did you gather the hints? It doesn't matter as long as you have the solution. So all the files on our systems typically have a very perfect structure, but in practice, the robust parsers that we use are like just gathering the clues, and at the end, when they reach the footer, do I have all the elements? Yes, the file is valid. That's how it actually works. And we'll abuse that again. So we want to abuse that. We know that we can move stuff around in which order we please so that the collision is happy and the parser is still okay. We don't modify the objects of the file, but we just move them around so that it works with the collision structure. So, for example, if you take a small file with a header, a body of some elements, and a footer, and you just add one comment, or a longer comment, or a lot of comments, and even some data at the end, these files are strictly identical for a parser. And in here, you just need to know where the boundaries are of your header, body, and footer. You don't need to understand everything inside. You just move data around. So you can, so this is why it's instant to go from one file to the other. Make sense? Skeptical? No? Feel free to. So if you take two files of the same type, they have a different header and a different body and a different footer. So now you study the landscape a bit to find some header that will work for both. So maybe if things are not so nice, you have to make the two images of the same dimension so that they have this to be to fit under the same header, or something like this. Or yeah, but still more or less the same content. Then you do a computation, the usual padding and collision, and then you take the body and footer at the right. You take the original body and footer of the original file without just copying the blocks. You just keep the header, you copy everything, poof, just after this, one after the other. And then you just align things so that the difference is creating a comment of different length, so that you either the difference in your collision will act as a switch to jump to one or the other content. And the other good thing is that the collision depends on this, but then this will always jump and you don't need to recompute anything. Make sense? So the suffix can change. The file will always be valid because it's valid on both sides. Then you can still update any of the content. So the prefix is identical. The collision blocks are depending on this and are fixed now. I mean, after the computation time. And then you can append whatever you want. So the hash value will be the same. It's just a block. It's just playing Tetris, and at the end you run the tool and you have the same hash because you know you respected the rules of the game. It's like a ski jump whatever is here, you just will always land at different distance. And whatever was in the original content, because in one case it will go here and then parse the same header, a comment that keeps that, then the body and the footer, it will render like this file. And here the jump is longer, and the parser will just land on the original body and footer of this file. So these two files, which have the same hash, will render as what you wanted them to render as, coming from arbitrary content, like Mimikatz and your holidays picture. Any questions? Yeah?
Just on the side before, since the collision blocks are randomized, I mean, how do you make sure that they can align with the common definition where the length is in the offset matching?
Well, that's a part of the trick, but we'll just exactly see now the collision that will enable us to do that. Because with fastcall, it doesn't make sense because it's full of randomness. Does that answer your question? Yeah. So that's why now we need the hypothetical weapon that I asked Mark Stevens. I thought I asked something weird, but so that's why we will do something poetry. Let's write a poem. So you can put leading space at the beginning, and you want to replace each of the 10th letter with the next letter in the alphabet, and it still has a meaning. The good thing is that you can do that mentally. You can say, oh, C is replaced with D, G is replaced with H. Suddenly you don't feel like a cryptographer. You can just say, hey, I know what it will come out. Now let's go for binary. 0 will be 1. Woohoo, you can add 1. It's not hard, right? Which is why it's pretty awesome. It's another IPC that is called Unicall. So we'll not compute it here. Unicall, has some specific restriction on the prefix. So if you start with the prefix of 20 bytes, exactly 20 bytes, I will explain why. You compute and it takes a few minutes. So this is what it looks like. So it will look like more cryptic. It makes GCC very understandable. See? It should take a minute or so. Maybe it takes a minute, I don't know. All cryptic stuff. See? Makes GCC very understandable. So again, if you don't understand what this is, maybe you don't want to watch Mark Stevens talk about Shattered. If you do, please be my guest. But the good thing is that I asked him, do you have an attack? And he was like, sure, check chapter 8 of my thesis. We'll see that. I'm glad he created a script to do it for us. And then at the end, the magic. I mean, he said it's not magic, but just tricks. Shouldn't be too long because we are almost at the end of the video. I mean, it's not a video, it's a terminal recording of text. So you can still copy paste if you want to. Yeah. And at the end, same hash. Thank you, Mark, for creating the script to do it for us. So at the end, what we do, we just have a prefix. Here is my prefix that is 20 characters exactly. And what happens? Okay, sometimes Unicall fails. In this case, just rerun it. Okay. And now what we have is we have two collision blocks, but our prefix is inside the collision block of the first file. And even more impressive, in the second file, we have our prefix and the 10th character was replaced by the next letter. So not only we can plan what we have in the collision block, and we can plan what is before and after the first difference, but we can also mentally think easily what the value will be. So it's like super powerful. And now suddenly you realize you can declare a structure before or after, and then you have a length here, and then you know that the value will be just incremented by 1. So Unicall takes a minute, or a few minutes. I mean, if your machine is not powered and you're running into a VM, it can take 20 minutes, okay. But this is like super powerful in comparison. Now we can really plan some structure. Does that make sense? So it's a true unicorn of a collision. It's an IPC where you can define data before and after the first difference, and you know what the values will be in both cases. It's really super powerful, super flexible, even though it only takes a few minutes to compute. So again, this is a part of chapter 8 of his thesis. These are other parameters of collision that were found in other research papers. So no, it cannot be at another offset of the 10th, right? Or if you can, I mean, it's really specific to MD5 properties, right? And I'm thankful that he created a script to do that instead of enjoying Greek LaTeX. And the other working cases are not easy to exploit. Actually covering them, he implemented 3 cases. So these parameters are in the script. And you see that they come from these parameters. And another one is interesting because there's a lot of difference after the first difference. There's a lot of plain text, the part of your prefix, the difference is earlier in the prefix, but here it's not +1. Okay, so this can be useful, but in general, the other one is much more easy to use because it's easy to do +1 mentally on the 10th character of your block. Any questions? Okay. So again, I mean, your prefix can be bigger than a block, and then the data before will just be as a prefix. It will just be there, and then the last part, the last block will be the one integrated in the collision blocks. So you can still have whatever data you want here. And again, this part doesn't matter. It just sets the initial value. So it could be the start of any file format you want. An important thing is that the last block, the length of this should be exactly a multiple of 4, which is why, because this is actually how these functions work. They work with blocks of 4 bytes in computation. So that's why I use a prefix that it was 20 bytes. Exactly. Otherwise, it will just not work. But it will just say, I finished my work, and then it doesn't collide. So, yeah, and okay, not so important. Okay. So Unicall is slower, 2 blocks, a few minutes, but the differences are in the prefix, which is super powerful. And now maybe you can see how you can exploit that. And that's what we're going to do. So, study the format specs and look for features you need to move blocks around and understand what's the header, how the format work. Then you choose if you can use fastcall, unlikely, but who knows, or just use Unicall. And then you plan your file structure. And then really important step, you create your mock file that has the structure you want, but just full of garbage, but that is not the computation. And you see the compatibility of that file. I'm telling you it's a big time saver, because here you see that there are like 9 blocks, which means it was a hash clash, which means it's hours of computation. And this is when I fail. And we're like, oh, 2 hours, cool, shit, I have to change a single bit. Okay, oh shit, 15 hours of computation. So if you want to say this step of actually crafting exactly the right structure and then checking the compatibility, imagine it has the same hash. Are both files working the way you want? You can even start your script with manipulating structure with these mock files. And then you do you cut here and you do the actual computation. Make sense? So why is Unicall so easy to exploit? Again, the first difference is surrounded by chosen text. So there are no restrictions to declare a structure and a length. And the difference is +1, which makes it very easy to predict. So with fastcall, you had the difference surrounded with garbage. And here you can easily say something like declare a chunk type and then a length. And in one case, you know that the length will be 71, and in the other it will be 171. There's no mistake. You run the computation, it will be what you ask it. It's like super obedient for a collision. So, as mentioned before, you first add a comment to pad things at the right block boundaries, and then you declare a chunk, a comment, and the length declaration would be exactly aligned with Unicall difference, so that it will have 2 different lengths. And then here you put the file, the body and the footer of the first file, which will be covered by the comment. And right after that, you put the body and footer of the second file, which means in one case, when the comment is shorter, the parser will see the header, signature, ignore comment. Here's my file and my body and footer. Then the file is complete. I ignore the rest. This will render as file A. And then in the case where the comment is longer, the whole content of the first file is ignored, and it will render as file B. Now the thing is, so yeah, what's this? Yes, and again, you can do that, and then you can make a script to automate that. Now, the problem is that the length of this is variable depending on the input file. So you actually declare another comment, and you hide the collision, the variable length comment will actually be used to hide the declaration of this comment. And the thing is, this comment here, the length of this comment, that actually depends on the length of the first file, but it's declared after the computation is done. So now, in the case where it's short, we have indeed the 3 structure comment that I mentioned earlier, the 3 comment structure that I mentioned earlier, one for the padding, one that is variable length, just to hide the declaration of this comment, which was made specially to jump over the content of the first file. Okay? Any questions? So it's not always easy. You have to know what can vary of how much, because sometimes the comments cannot cover the whole length you want. On GIF, a comment can only be, in theory, of its length is stored on 1 byte, which is like 255 characters. It's very small. On JPEG, it's 2 bytes. On PNG, 4 bytes. You can jump wherever you want. So that's why there are very few restrictions for PNG, and that's the one we were going to exploit. It's also very interesting to explore different tools, because some tools may create a structure from any input, may create a structure as output that is very easy to hack. And for example, MuPDF really creates a structure of PDF with all the page index at the top, which is exactly what we want to turn on and off pages. So it's like it's making a very generic structure very easy to hack. Or in the case of GIF files, you want 2 images to have the same properties. Well, the shortcut is just to make an animation of the 2 frames. And in this case, the 2 frames will be declared in the same header. And then you just use an animation making tool, and then you separate the frame by just locating the right offsets and copying the buffer out, saving a lot of time compared to handling all the cases of PDF or GIF or anything, you know? Trust me. Which is great, because then you can have a very small PDF or a totally encrypted PDF using the latest feature, and you have to have a powerful tool like MuTool that is able to handle all this in input and give you something very ready to hack as output. Is a huge time saver. So let's look at PNG with Unicall. So PNG file format is extremely regular. It's a signature and a sequence of chunks, and all these chunks have the same overall structure. Underneath, they have different structure, but that's not what we need to know. We don't care. So the PNG signature is enforced at offset 0, and it's always the same 8 bytes, which have some meanings, but we don't care. We know that this is what makes a valid PNG at the start, and we just keep 8 bytes. And then we have a sequence of chunks. And this is what this is all the body, and even the footer is a chunk. So you skip the first 8 bytes, and then you copy everything, and you have all the chunks of the PNG. If it's a standard PNG, which means no garbage after the footer. But even in this case, we don't care. And the chunk is declared with a very same structure. First, a length, which is a big endian, on 4 bytes, and type that is on 4 letters, ASCII letters. And then there's data, which is of the given length, which can be null, like the footer is of null length. And then there's a CRC that covers type and data, and these CRCs are actually ignored in practice by viewers. Not by PNG modifying tools or anything, but by you standard viewer, your browser, they are ignored. So it's very simple structure, and this covers, you have the signature, then you have a sequence of these, and now you can go through a PNG by yourself. And we're actually going to do that manually. Just one point, we say that the type is on 4 letters, and if the first letter of is lowercase, then it's ignored. So if you call it Aling, Skull, Skip, Ange, whatever, and the first letter is lowercase, this is acting de facto as a comment. So if the first letter is uppercase, then this is critical, and there are only a few critical chunks, which are always present. Image header, palette. A palette is not always present. Image data, image end, which is a footer. Apple has a custom PNG, which has a different critical one, but of course they had to do something different. There are some lowercase, so non-critical chunks that can be, that exist, but you can remove them and the file will still be valid. You just remove some extra information. And then whatever you put, as long as it's 4 letters and the first is lowercase, it will be ignored, acting as a comment. And remember, we said that the length is on 4 bytes, so you can skip gigabytes of data with just putting a lowercase comment, a lowercase chunk type, which makes it a comment. So let's just go through a PNG ourselves. This is just this cross, this is the whole file. as I mentioned, first there is a signature, then a sequence of chunk, which is a length, a type, and a CRC. So the length, so first look for the signature, and then you will have a sequence of something that is the end of the previous chunk, which is a CRC, so something random. Then you have a length that is like usually 0, 0 and something, and small value. And then for letters, so alpha string 4 bytes. So then we just need to, and we just take the length of this, and we just need to skip. And we don't care about the rest of the data. That's how we will just skip through the files. So we have the length, we skip, we have CRC, length, and we skip, and then we end up here, and this is the footer. All the rest is part of the PNG, but we don't care. So we can just skip some, all the memory range. This is what we care for these files, for this file. And indeed, if we check the types, we have image header, palette, image data, image end, which are all critical. So you can even describe them like this. And we say it's chunk, so you could easily add your own chunk in the middle, which is why this is exactly the minimum. The script is available on the URL, on the repository. This is exactly what you need to just either read or regenerate a PNG. You don't need anything else. And now, remember, we know that lowercase chunks are ignored. We can give them whatever name we want as long as the first letter is lowercase. And we need 3 chunks. One for alignment, one for collision, for declaring a comment with exactly aligned to the 10th character of Unicode at a given block. And then the chunk that is added after the computation that will jump over the content of the first image. And the rest is moving around chunks. And this is what, with the script, this is exactly what we can do. We read the file, and then we add up just 2 chunks. And the chunks are generated, and you have still a valid PNG because you're just respecting the structure of chunks, and they are lowercase, so they are ignored. Any questions? Someone wants to try or not really? Right now? You will try? Who wants to try? We're doing right now? Okay. Sorry for the others. Sorry, question? Oh yeah, everything is available. Don't worry. Yeah, that's covered later. Okay. For executable, you need to know hash clash. It's not Unicode. Spoiler. But so with just the script not here and just this declaration, you will add 2 chunks that will be valid, that will be ignored by parser, and that makes the whole PNG file still valid. And you see that you can start to plan your structure for collision. Because in the end, it looks like this. This is what you want to achieve right now. Mission. 1 segment for alignment, then 1 for collision, with exactly the byte at the 10th, the length. Declare. So why is it on this byte, on the second byte of the length, and not on the first one? Because you still want to jump over the blocks. And if the difference will be +1, so in the end, if you difference is just +1, you will land just at 1 byte or the other, and you cannot declare a chunk with this difference. So what you want is indeed to just jump to like C0 and 100 later, 1 C0. And this gives you enough room to declare a chunk to jump over the content of the first image. I mean, the file and body. The body and footer of the first image. And spoilers, you have the whole working script, so on your mark, Floyd. Ready? What?
Still compiling, I had an error, and it's compiling again.
Why is it an error of compiling? I mean,
so hash call for macOS has to install Boost. Now it's and that takes a while.
Okay.
Now,
I sent the prerequisites before, just saying. So who's trying? Not so many. I feel that so since most of this room is not trying, we should still skip ahead. What do you think?
Go ahead.
Go ahead. Okay.
So
so we maybe cover more. Any other questions? Or maybe we can take some time to explain more something we covered already? All good? So remember, Kaitai is pretty good to just explore the difference in files, especially, as I mentioned before, you don't need to have the whole understanding of the structure, and this is just the minimum grammar that you need to explain, to tell Kaitai to just describe the chunks and not the overall structure. So in this case, you can see here it's not, you can see that it's actually just showing the content of the chunks with the length, and you can see the difference that here the length is 75 and here the length is 175 of two colliding files. So really don't hesitate to trim down the grammars of Kaitai, so it's just what you want, the high level structure and not all the nitty-gritty details. And you can edit the grammar directly in the IDE, and in this case, the modified copy will be automatically saved in local storage. So you can just do it online, and you open the PNG grammar, and then you remove some stuff, and it will be saved automatically, which is very convenient. So it's very important to understand the landscape. Remember, I said to test the mock files on the various software, because you don't want to compute the collision for something that actually only works on one viewer, except if you target only one viewer, but it's good to know in advance. And at least all PNG's viewers seems to ignore CRCs. And most PNG viewers what we want is that instead of starting with the header, we want to start with the alignment chunk, which is against the spec. And most viewers tolerate that, except the Apple ones. Even though the Apple ones introduce a non-standard chunk. So with this trick, you will not have Apple compatibility. If you want Apple compatibility, then you need to have the image header chunk first, which means the dimensions, the color space, if it's paletted or not, will be before the collision blocks, which means your two colliding images have to have the same properties. So it's not like any PNG with any PNG. It's a drawback, but at least you get really, in this case, PNG full compatibility with all viewers. Yeah, question? No?
I'm just trying to do the PNG.
Okay. Another thing is I said that they seem to ignore CRCs, and by default, when you have MD5, same MD5, you will not have same CRCs. You can do that. You can add an extra computation. But the other thing is that on one case, the chunk where the difference are, you remember the declared length was longer. So actually at the end of each chunk of different length, you can actually compute the CRC and you can have colliding PNGs with perfect CRCs. But in this case, don't forget, before your computation, because the collision blocks are here, to actually put the exact CRC of your alignment block. Because that's before computation. Just don't do that mistake. Here it's only a few minutes of computation, but again, really plan your files in advance before the collision. Really, the collision is at the last moment. When your files are ready, the compatibility is good, you get the prefix and you do the computation, and then you save yourself some hassle. Any question? Okay. So, for the courageous among you, we'll move on. But for courageous among you, congrats, certificate Pedium. So yes, you can have correct CRCs in PNGs. The script that is on the script, there are two versions of there are several versions of the colliding PNG in the script that is on my repository, so you can see them. They are increasing complexity, but it's not so hard. And now, the other type of collision, chosen prefix, which will cover executables. So far we have two identical prefix collisions. They take a single input, the common prefix. The problem is that some formats have hard-coded offsets, like P executables, and or they don't tolerate early comments. So you cannot put the comments early, so you cannot put all the alignments and collision blocks before there is some critical data like ELF files. And with the same prefix, you have the same header, so you have the same file type. With the same header, you have the same metadata, and there are extra problems. So, and right now, well, yeah, this is just to say ASN1 is not possible. So now the ultimate attack that exists is a chosen prefix collision, hash clash, that we call hash clash, but in practice, hash clash CPC. And when a chosen prefix collision is implemented for a hash, it's considered broken, because then you take, we'll see, any pair of files and you have colliding files. So this is our third block in our game, the CPC hash clash. So it takes a few, there is 72 hours core hours to compute, if you're lucky, again. And why if you're lucky? Because sometimes some steps stall and they have to be restarted. The good thing is now the restarting is automatic, but it just has to retry some stuff, and it can take only a few hours to a lot more. Again, this is computation, collision computation. But at least now it's much better. It's really, you just have to do one thing and wait. Wait a few hours, depending on how much horsepower you have. And it will automatically detect that some step will have stalled, and it will retry the next step until it's finished, hopefully. So right now, this is a collision when you choose to collide just the word yes and no. So what do we have? We have some padding until the end of the block, but the last block is used, the 12 bytes are used for randomness purposes. And then there are 9 blocks that are, again, full of randomness, with a very few differences on each side. But at least whatever was here doesn't matter. So, and it's 9 blocks. The fewer the blocks, the more the initial step will take. So 7 to 9 blocks takes a couple of hours. If you want just one block, then it takes 400,000 hours or something different. So this is doable, right? And again, if you think about something like PNG command that can jump over a very large distance, it's not a problem. It's just that you say that you cannot have that easily in 2 blocks like Unicall or Fastcall. Make sense? So how does it work? You take 2 files, whatever they are. Again, their content doesn't matter. And the padding, the smaller will be padded to the longer, and then 12 bytes will be shoved out of the last block, will be removed from the last block for computation needs, for randomization needs. And then 7 to 9 blocks will be added. They have differences at very special offsets, but in this case, we don't care, because whatever was before could be just anything. Could be a Windows binary and a JPEG. And this will always work. This is super powerful. You take your prefix, you run the script, that I mentioned, you run the script, you wait some hours, and it's done. Same hash. And of course, at the end, they have the same length, but the start is totally different, right? Because it's what you set. And you know they will have the same hash. So it's super powerful. So which is why, at this stage, a hash is considered broken, because you can really collide an arbitrary amount of files. An arbitrary amount of pair of files. It's just that it takes the same, minimum amount of time each time. There's no shortcut to reuse. There's no to reuse a computation. So 7 to 9 blocks, a few hours, and the difference are irrelevant. It's almighty, but slow. No, okay, this I should have removed that. Now it's automated. So you used to require yourself to monitor and kill the steps. Now it's automated, thanks to Enrico. So again, the two arbitrary prefixes don't matter at all. And then it's just blocks being appended to each of the prefix you gave. Make sense? So, yeah, if you want, sorry.
So if you find a format that has ending in the block.
No, you can just put two entirely valid files of their own format, as long as the file formats accept appended data. I mean, yes, because there's the footer that says, hey, this file stops here, and it's good. I mean, and most file formats tolerate appended data. Very few actually check, or except if there is a signature, right? Like, which makes sense, but yes. But most standard file formats, PNG, JPEG, GIF, P, append, whatever you want, it will be ignored. And whatever you had here, it will work. Any other question? So, yes, I was as mentioned, the fewer the blocks, the more the computation. If you didn't want to have 7 to 9 blocks. Again, one single block, which is really very compact, right, for a collision, but it takes a lot of time to compute. So, as I mentioned, this was just a question, if you have two file formats that tolerate appended data, compute done. It's like super powerful. But again, you have to redo that every time you modify a single bit to either file. So now, let's just see the impact of both IPC and CPC. In IPC, you have the two contents that are always present in both files. So when you do that, evil and good, the file has a weird structure and you leak the content of if someone looks inside the file, it's really odd. But if no one does, you still manage your exploitation. Like if it's JPEG and Mimikatz was still run, right? And here, in this case, you don't leak either, but of course it's slower. Now, the file here is totally different. Like, it shows when you open with a hex editor, but most people don't, I mean, it's hard for me to believe, but most people don't open a hex editor and every file. And by the way, if you apply to our team, please, I will open your resume with a hex editor and I hope to find interesting things. So just to make that clear. Anyway, most people don't. So from a parser perspective, these files are just standard, but from the internal structure, they're super weird. And here, in the case of CPC, the start of the file is exactly what you wanted, so they're probably totally normal. And it's just the end that is giving it away. Again, same length, and so on. And here, you can reuse the computation to put whatever content you want. And here, and for the CPC, you have to recompute every time. Make sense? Any question? Okay, just ask. So what about trying both for the Windows executables? Combining the reusability of IPC with the flexibility of CPC, which takes longer to compute, but let's do it once. And then having something automated. So we do, in the end, when you do a CPC, you create a prefix, different two prefixes which have the same hash. So you can reuse that as input for an IPC. And remember, it's because it's block boundaries. As if it's the same hash, you can swap them. So this way you have the total flexibility for the header that you want. It's just that it's longer because it's 7 to 9 blocks and it's longer to compute. But then you have no restriction from the start of the file. And then you can reuse the same reusability. You can use the same reusability trick to combine it instantly with any content. Does that make sense? So now we can have multiple file types, and we'll see which can change them. Yeah, any question? No? So let's explore a bit the Windows executable file format, P and collisions via a chosen prefix that is used like an IPC. The CPC used like an IPC. So a P file, a portable executable file, starts with the DOS header, it has a magic at the first byte. And then at the end of this, it's actually a 64-byte block. And at the end, there's a pointer, which is, these are the only two important things for modern OSs. And this pointer points to the P header that starts with the P00 magic. In between, you have the DOS stub, which is this 16-bit code that just prints the strings. This program cannot be run on MS-DOS or something. And you have, with Visual Studio compilers, you have the rich header, which finishes with the rich magic, which contains compilation information. What is the other thing in the DOS header is not important, and the DOS stub and the rich header can be removed. Everything critical is in the P header, especially, I mean, the architecture and everything, if it's kernel, whatever, and also the section table, which indicates which range the sections, basically which range of the file to load at which address in memory with which permission. And we don't need to change the address, but just it says the offsets, where to get these ranges in the file. So again, we don't care about most of this. The DOS stub can be removed, the rich header can be removed, and the P header can be moved around as long as we modify the pointer here. And the sections can be moved further as long as we just update the offsets in the section table. We don't need to change the rest of the section table. We just need to tell the loader to find them somewhere else, further. So now, the DOS header is generic. We compute with, we just have two versions of this pointer to point to different offsets. Here we have the collision block for the CPC. Now we put two P headers next to each other from the original files. And then we copy the set of sections. Again, it's just finding their offset and moving data. And then we just need to adjust. So we need to have the P header exactly at the offset pointed by the prefix because these are fixed because of the computation. And then the sections will be, the section groups, sets, the two sets of sections will be copied next to each other because we don't care. And you just need to adjust the offsets in the table, in the two section tables of both P headers. Does that make sense? So you can really collide any pair of binaries. It can be console, GUI, different architecture, because the P header is what defines all these details, and the DOS header is just totally almost useless, just the MZ and the pointer. Make sense? So this is more complex to compute, but it's a single step. It's a single launch of // CPC, and then you have reusable prefix that are available on the repo, and you can collide. Yeah, I collided Mimikatz and Cuphead because it's two interesting games. So again, you can have two DOS headers with enough difference to cover the 9 blocks of difference of collision, and to skip the first P header. So you just take the normal size of a P header, and you just need to copy, once you have done the computation, you just need to copy the P headers, the sections, and adjust the section offsets. And then you get instant collision of any pair of Windows, Xbox, whatever, executables. I'm not sure on how many systems P is used. Shame on me. Surface. It's still Windows. Any questions? Any break or something? Yes? Oh, okay. Break. Okay. We're almost done because there was no hands-on part, so let's take a break. You have some time. Let's get wasted. Oops. Okay, we move on. I mean, we are actually done, so yeah, we're done. So, chaining collisions. As you mentioned, as you maybe noticed earlier, I mentioned that we did 600 collision in a file, or we had a 4 file types collision. It's not, of course, with a single collision. So if you think about it, a single collision makes two different contents have the same hash. So two different contents have the same hash, and then it's like collision. So for a collision, it's like one content. So you can actually chain them like a tree. And the top nodes have to be an IPC, can be an IPC, and then you can use CPCs or Unicode. And then you can collide more than two files. And n collisions makes n+1 content collide, if you want, if it makes sense to you. But it's possible. So a few examples are the ones I mentioned earlier with three CPCs chained as a tree to collide 4 file types of different size. The poem that I mentioned earlier actually chained 8 unicalls. So it's unicalls, which is identical prefix. But in this case, unicall is behaving like a CPC because the difference that is displayed is a part of the prefix and the collision block because it's unicall. So this is actually displaying the start of the collision block in the PDF because it works. And you can chain them, so that actually you can see the difference. And in 2007, Mark Stevens did that by predicting giving the hash of the future American president, which covers Paris Hilton, by chaining 11 hash clashes. But he wasn't elected as far as I know. Just for mention, to cover everything, let's see the properties of shattered, which is a SHA-1 IPC. So, as far as I know, it was computed only once. And the differences are at the start, and right at the start and right at the end. So basically, before the first difference, you control, because it's part of the prefix. This is what we exploited. And the official proof of concepts are JPEGs in PDFs. For the reason I mentioned earlier, if you want to exploit PDF, you have to deal with 6 families of viewers. And one trick that works in a family will not work in the other family. While all them, PDF embeds JPEG natively, like you can have a JPEG in the file exactly like it would be as a standalone file, starting with the JPEG magic and everything. And they all use libjpeg, which is de facto the JPEG software. So if you find a trick for libjpeg, it will work in PDF, and even if it's at collision level, and it will work in all PDF viewers. So you gain full compatibility thanks to the landscape. The landscape of the PDF is split into 6, but then if you use a JPEG, you're back to a single implementation. And again, the JPEGs are against the standard, but they are okay with libjpeg, so the files are just working everywhere. Does that make sense? So, as I mentioned, the shattered block have differences everywhere, but most importantly, just at the beginning, at the very first byte, which means you declare a length of a comment. So you have first a comment here for alignment, as usual. Then you declare another comment, and you declare the length of the comment, one byte outside of the collision block, and one byte inside, and this will be of variable length. So it's easier, it's harder to exploit than Unicall, because you don't control after the difference. And again, you certainly don't control that, because this took 6,000 years core to compute. A few Olympic pools to boil, just to put that in another perspective. And then you jump, and then same technique, except that here, JPEG comments, the length is only on 2 bytes, so you cannot jump very far over a whole JPEG if it's too big. So you split your JPEG into segments, and this is actually what I talked about 2 years ago here at Black Alps. So if you want the whole findings regarding shattered, this presentation, because I actually had a bit more fun with PDFs, but at least the idea is the same. So what do we know here? We know that we don't control the bytes after the difference. So we cannot have a length, then a type, because the type is in the randomness. So we need to exploit the formats that are the kind of temp, type, length value. Value is data. So the length declared after the type and not like in PNG, the type after the length. Does that make sense? Why? And there are very few formats that are type length value that are very common. JPEG and MP4. Which, I mean, MP4 can actually be in both style because of some tricks, but anyway, it works. So you know, because of this, even if there's a single prefix that was ever computed, if you say, hey, let's compute another prefix, I would say, hey, let's do the MP4 one, so that we know that we can collide with SHA-1 MP4 videos, because the trick is the same. And if one day we have a SHA-2 collision, well, we already know which trick will work and which trick won't. Make sense? Actually, the JPEG trick, I use it on 3 hashes. SHA-1, MD5. It was the same trick, basically, to this FE comment and the length. It's the same. And before I worked on SHA-1 and MD5, I originally worked with Jean-Philippe Masson on modified SHA-1. That took less time to compute. So the same trick, the same file tricks is reusable across different hashes, which is great for finding new tricks. So if you find, so I would show later, if you find like you collide, for example, binary protobuf, then you know that the moment someone gives you the ability to compute a SHA-1 prefix or anything, then maybe you will know in advance whether it's exploitable or not. So it's very beneficial. It's not just one big computation. The tricks are independent from the computation, right? Because they kind of don't care about each other. As long as the byte has the right value and as long as the blocks are aligned, both are happy. Does that make sense? So there are 3 attacks on MD5, 2 identical prefix and 1 chosen prefix. Fast call that is hard to exploit because the difference are in the middle, but it takes a few seconds. And unicall, which takes a few more time but has a lot more power. And then hash clash, which where the difference are irrelevant, which takes a lot more blocks, but is chosen prefix, so two prefixes, whatever they are. Again, all these attacks, they append random looking blocks with tiny differences, and there's no other kind of attacks. There's no possible the way to do something in the middle before be at the top of the file, or there's no possibility to do ASCII only or this kind of thing. It's always compute append blocks of randomness with tiny differences. The problem is that, yeah, so there's nothing like this. People ask me, do you have another trick? And no, there's not. I mean, not to my or Mark Stevens' knowledge. And the problem is that because there was a chosen prefix attack on MD5, it's considered dead. So there's like no research. Everything I mentioned today attack-wise was documented in 2008. So I just adding new tricks, file format tricks to it, but no one is interested in publishing something new about MD5 because it's considered dead anyway. A reminder for the exploitation patterns, so the standard chosen prefix, the IPC, and then the combination of both. The typical layout of abuse with the command for padding, the collision commands that is covering, that is with a variable length, and then the command to ignore the content of the first file. So we don't consider MD5 a cryptographic hash, but more like a toy. Actually, I don't know. I don't know if you're familiar with that, but let's see. Can I have? Do I? No. There's no internet. There's no internet. Oh, because okay. There's no internet. Yeah. Okay, that's great. Yeah, so not mentioned, but really a toy. MD5 is total collision. Mako, he implemented a Mega Drive ROM that computes an MD5 collision. And I ordered a special programmable cartridge. The first thing I ran on the Mega Drive and on that cartridge was computing an MD5 collision. It takes 2 hours. You just need to put the cartridge and press and load it, and after 2 hours you have the MD5 on the screen, which kind of made my kids disappointed because they wanted to play Shinobi or Sonic. But it works. And the funny thing is that the Mega Drive is actually older than MD5, so it's like something from the past that is able to bring to break something that was considered cryptographically secure in the past. So it's very interesting. And when I said that to Mark Stevens, he was like, "Will you do a Nintendo version?" 8-bit. Usually we run out of time here, but it depends if you're really super tight, or I can actually show fast call exploitation, which is a bit funky, but how do you feel? Feel free to leave. But it's just we have some time, and I'd like to cover. So this is extra stuff if you're interested. I will not. That's covered the JPEG exploitation, MP4, and so initially, just for your information, when I gave this workshop initially, that was part of the main stuff, not extra, and that was a bit too much. So recap on fast call. Fast call has this difference right in the middle. So you need to be able to have a single byte that is all a valid structure and a valid length. So it really sounds impossible, except for one thing. GIF, whatever, GIF. It's called GIF. It's supposed to say GIF. The specifications are a bit old. And it works, but because you cannot put a comment before the header, the files have to be the same metadata. And the shortcuts for that is to make an animation out of it, which makes the two frames have the same dimension and the same header, and then you just separate them. And actually the trick is that you display actually both frames, but one you put it a 10-minute delay. So, and then after 10 minutes it will show the other frame, but technically it works. You just see two different frames. And if I have this document in Google Doc, after 10 minutes they show the same frame. Because 10 minutes is the maximum value of delay you can encode. So GIF has a bit of a weird structure. So fun thing is that the chunks of GIF are separated with punctuation. So that's the declaration of the extension image, and it's finishing with a semicolon. And the important thing is that there can be a palette that is global or local. And the problem is that the comments, they cannot jump very far because they are declared on a single byte. Single byte, like fast call, which is good. But you don't have a lot of distance. So it's important to see, when you explore your file format, to see you know that a comment can only jump to 456, 55, but to see what is variable and what is not. So the palette is variable. And then the extensions, the graphic control, comments is important, and the application. Okay. And here, the local palette, you can remove it, but the image data will grow a lot, depending on the amount of pixels. So the problem is that, how can you jump over an image if you can only jump 255 bytes? Now, in this structure, the comments and the data are stored in the same sequence of subblocks, where you have a length, then the amount of data, and until there is a length that declares 0. So this declares 7, and the data is comment. So it just decomposes a comment containing 7 characters of comment. And this is exactly the same. 1 character, that is C, 4 characters, that is these letters, and 2 characters. So these two structures define the same data via the GIF subblocks. So this is why you can only jump not too far. You have the length of a comment in total is unknown in advance because it's made of this. The important thing is that comments and image data are stored with this structure. So that's a very clever suggestion from Mark Stevens himself, where since they are stored in the same, with the same substructure. You actually make the comment extend in the image data. And suddenly the image data is seen as a comment. And in this way, no matter the length here, it's just following this substructure of mini jumps. So here you have comments, and then suddenly you just skip this part. It is always 10 bytes, which is okay. And you make it jump over here, right in here, and then it will jump all the way until the end, taking it as a comment. And this is a wonderful technique, and that was his suggestion. I wish I had, I hope I will have such a cryptographic suggestion one day, because probably not. So you declare the delay between images, which is okay, and then you declare this comment that will either just end as a comment or just skip over this 11 bytes or something, or 12 bytes maybe, I don't remember, in the image data. And in this case, in one case, it will expand the comment and just display the second frame. Or in the other case, the comment is shorter. We set a delay of 10 minutes. So you cannot interrupt the parsing here, but you can say, hey, display it for 10 minutes, which kind of does the trick. So in practice, it gives that. You define a command right before you fast call. So here it's fast call, right? It's very quick to compute. You jump at the length exactly. You want to jump at the end of fast call, or the last difference of fast call, so that you already cover the maximum length. Because again, you cannot jump very far with this subblocks technique. And then you jump to different values, and you know the difference is always the same. You don't know the values, but you know the difference will be always the same. 80 in XOR in this case. So it's the same bit. And you just display this image, which again, GIMP will tell you. So 6.5 for every, it's a hundredths of seconds, which is why the maximum value makes 10 minutes. So you just normalize. You want the common header, you just want to normalize the two pictures, just make an animation, increase the delay, and then just before the second, just put this comment to skip before this to jump into the image data, to slide into the image data. It's a data sled. Okay? So in practice, it gives that. Let's say it's simplified. The declaration, you jump, just here, the collision, and the last difference is here, and then you jump to another subblock, and this subblock makes it slide into the data. And again, it's because there is this unique subblock and weird structure from 30 years ago. The initial specs of GIF were in 1987. And this works with a single byte trick. So declarations are separated from length, but it's compatible with fast call. You cannot skip too long, but image data is stored with the same structure. So you extend the comment in the image data, and with the max delay, you just prevent it to show the first frame as much as you can. If you have a better hack, I'm all ears, but here you just combine the two images and you just insert this weird comment and it works. And you don't need to reprocess anything about palettes, local palettes, and all the complexity of GIF, because it's actually pretty complex. So this is a hard certificate, and good luck if you want. Yes. I said that there's no more research on MD5 attacks, but there was this reuse of attacks in 2015 on protocols, which was pretty clever, and maybe I will extend to that, but still I think it's enough for today. And just this year, there was a new paper that introduced practical chosen prefix for SHA-1 in supposedly, I think, 3 times the time of shattered, so probably not on your Mac. But maybe someone had already implemented. So in practice, it could be possible to compute chosen prefix for SHA-1. It was a new paper released in May, I think. And yes, thanks. I mean, with the documentation, there were these flags covered with covering new file formats, including this one, I think last month, which was about protobuf, binary protobuf. So using Unicode to hack binary protobuf, and both write-ups are very interesting. One, because the first write-up did jump over the collision block, and then there were payloads. And the second write-up actually tried to find the smallest payload that would work still in the prefix before the collision, the actual random part of the collision block. And so like one is like, cool, nice. And the other is like, oh my God, I didn't know. I mean, like really it's maybe over the top, because you typically want to jump over the collision block and then you do your land safely and do your stuff. But here it's like, nope. Nothing after the collision block, no suffix, which is pretty impressive. And yeah, thanks for making it this far. We're early, so if you have questions or anything or comments, please ask. All good?
If you want to use secure hashing, or you should go.
To index files or just to?
Yeah, general. You would say SHA-1 is also kind of.
Well, again.
Not sure how secure it is.
Yeah, but if there is a lot of data and people don't know what data there will be, they cannot plan in advance. If they have the time to prepare and to submit files, then SHA-1 on the fly is absolutely impossible. So it's still okay to use SHA-1 on totally random stuff, as long as you don't give the attacker a possibility to send a file they created, right? In this case, we are never able to, oh, there's this hash, now let's do something with that. It's always prepare in advance, send a good one, and then get whitelisted and send a bad one.
Yeah, if you can choose, you always want something newer, because once SHA-1 gets more broken, you might not be as quick with changing your hash algorithm. So
well,
don't use any of the old stuff if you don't have to.
Yeah, but at least make it possible to change, because one day SHA-2 will be broken and something, right? So it's more like just make it easy to upgrade to the next one. But still, if no user controls anything and you just want speed of computation and you have to do a lot of comparison that nothing was modified, then MD5 is still okay. But yeah, just make sure if there is something that is controlled by the attacker, then, and they can prepare stuff in advance, yes, you're at risk. And you can prove it, give the files. I didn't mention here in this talk, but basically the whole background behind this research was that last December, there was some official paper that says MD5 is fine for incident response. And Mark was like, started a long discussion on Twitter, explaining stuff. And I was like, I prefer to let file do the talking. Hey, instant collision of PNG, instant collision of P, instant collision of JPEG. So what files are you going to send someone in jail with? So like, yeah. So I send you a file you want, but I hide malicious content in it. And then I say, hey, this guy has this malicious file on his hard disk, and if it's indexed by MD5, which as far as I remember is still the default option in NCase, then you can be incriminated for that, for having this file. You can say, I didn't have this file. Does that make sense? Final comment? Okay. Okay. Thanks for your attention.